Swayam Prabha. Digital India. Educated India.
Okay, so we said that we'll have the three-phase supply, A, B, C phases with the neutral, and we are going to have 3 diodes which are somewhat like this, and we are going to have a load between the neutral and the star point of the 3 diodes. Right, this is what we said, and we had called these 3 as D1, D2 and D3 respectively. This was VAN, this was VBN and this was VCN. We called this point as the neutral point, and I may call this as some O, doesn't matter. So we are going to have essentially the current flowing in this direction. This will be the load current, which is unidirectional. Right, because either D1 will conduct or D2 will conduct or D3 will conduct, depending upon whichever is the most positive voltage at that point in time. If I say that this is what is my zero line and this is going to be my A phase, B phase will be phase shifted by 120 degrees like this, and C phase is going to be phase shifted by another 120 degrees like this. This is how it is going to be. So whichever is the most positive, that will conduct at any point in time. So if I say from here until here, I am just showing it as though it is exactly the same magnitude, but I just want to differentiate between the blue color, green color and the black color what I am drawing. That is the reason I am just drawing it as though there are 2 lines. So this is how the load voltages are going to be, and we said that normally I am going to have D1 conducting from here to here, D2 conducting from here to here, and D3 conducting from this point to this point. Right? So each of them is going to conduct only for 120 degrees, and if I assume that it is resistive load, I will essentially have the load current, or like if I call this as I load. So I load is going to look somewhat like this. So I have to just take this point here and this point here. So I will have essentially the load current showing up like this. This is how the current will be for R load. This is going to be for R load. Whereas if I am looking at RL load, only difference will be the peak will not coincide exactly with whatever is the peak of the previous one. So it is probably going to be shifted slightly, but by the time, it is changing over from D1 to D2, it also depends upon what is the voltage across the resistance, because we actually have to write the equation again. Vm sin omega t equal to Ri plus L di by dt for RL load. If it is RL load, this is how it is going to be. So I have to look at whether L di by dt will have to pitch in along with Vm sin omega t to meet the needs of Ri. So if Ri happens to be higher at this point where it is supposed to switch over from D1 to D2, if by chance Ri happens to be higher, I am definitely going to have probably the D2, that other one will not be taking over completely. So I may have actually further the inductance forward biasing the outgoing device. So we derived the expression for the voltage when we were talking about R load. When we talked about R load, we basically looked at the voltage something like this. It actually went about like this. This is how the voltage was. So if I look at this point, if I say this is omega t and this is 0, so this point is 30 degrees and this point happens to be 150 degrees because each of the devices conduct for 120 degrees. So I'm going to have essentially 120 degree conduction for each of those, and that is the reason we wrote actually 1 by 2 pi by 3 as the averaging quantity, and we wrote this as Vm sine omega t. If I want to take up Vm as the line to line voltage peak, normally that is how the three phase systems are specified. So I might have to write this as Vm by root 3. So that Vm happens to be line voltage peak. So in this case I should say Vm equal to line voltage peak. Whereas Van will be Vm by root 3 sine omega t, and I have to integrate between 30 degrees and 150 degrees, which will be pi by 6 to 5 pi by 6. That will be the limit. So that will actually give me whatever is the value of voltage that I will get for this. I think it happens to be 3 Vm by 2 pi. I think something like this you should be getting. Check it out. Any. That's what Vm is, the line to line voltage peak. Line voltage peak or line to line voltage peak. So this will be the expression for three phase half wave rectifier with diode. Right? Now let us try to go for half wave controlled rectifier. Right? So I am going to have three phase voltages somewhat like this, and I am going to have one device here, second device here, and third device here. This is the neutral point, and here is the load. So this is the load, and I am going to have this as the connection between these two. This point is O. So I would name these devices as T1, T2 and T3. So this is VAN, VBN and VCN. These are the three phase voltages. So I should realize that had it been a diode, we had shown the conduction would start exactly at this point, which is actually at 30 degrees. It is not at zero crossing of VAN, it is rather at 30 degree point of VAN. So I should always calculate the delay angle with reference to where the diode would have conducted. If the device had been diode, where it would have conducted, that happens to be delay angle equal to 0. So the reference will always become with respect to, it will be calculated always with respect to diode. If the device had been a diode, it is exactly starting at this point, which is corresponding to omega t equal to 30. If I say at omega t equal to 0, my sinusoidal voltage corresponding to A phase is having its zero crossing. Right? So when I actually draw the waveform for this corresponding to alpha equal to 30 or alpha equal to 60, how do I specify that? I am just trying to emphasize that. Okay? So if this is one of the phase voltages, so these are the 60 degree points, right? And I am going to have the second phase somewhat like this, which is very light. Maybe I'll at least use orange. That may be better. Right? And the third phase is here. This is how it is. All the three phases are here. Right? Now let me call this as VAN, this is VBN, this is VCN, and this point I am specifying as alpha equal to 0 degrees. Because that is the point at which D1 must have conducted. Instead of T1, if I replace that by D1, it would have conducted at that point. So I am calling this as alpha equal to 0. So I should calculate all my delay angles with respect to this particular reference. So if I am talking about alpha equal to 60, for example, this is what is alpha equal to 60, because this is exactly 60 degrees away. So I should say this is alpha equal to 60 and T1 will be fired at this point if I want the delay angle to be 60 degrees. Again, the delay angle is incorporated to reduce the voltage, what I would get as the voltage. Let's see how it gets decreased. So this is going to be alpha equal to 60. So if I fire T1 here, 120 degrees away from this I have to fire T2 for symmetry, because VAN, VBN and VCN are phase shifted from each other by 120 degrees. So I necessarily need to, this is 30 degrees, this is 60, this is another 30. So here is where I have to fire T2 and here is where I have to fire T3. This is how I have to fire each of the devices. So I have to go exactly by 120 degrees interval. And in this case, that's why in three-phase converter, we will not give a firing pulse whose width is 180, rather we will give only 120, because we would not like to give the firing pulses to two devices simultaneously. We would generally like to give only one device at a time, and T1 will be given for 120 degrees, T2 will be given for 120 degrees, T3 will be given for 120 degrees with high frequency ANDing and pulse transformer, pulse amplification, everything. The same kind of circuit will be adopted. Pulse width is 120 degrees. That's all is the difference. So let us say I am firing this at this point. Right? So until now what was conducting, I don't know. But the moment I fire this, hopefully this should start conducting, because anyway I am in the positive half of VA. So it should be able to get forward biased. So it will continue definitely until this point for sure. After that, hopefully B should have taken over, provided it had gotten firing pulse. But I have not given the firing pulse to T2 until here. I am giving the firing pulse to T2 only at this point. So until here, if nothing else is conducting, between the neutral and O, between the two, if I try to look at the voltages normally, I am going to have this particular device T1 forward bias definitely until here, no doubt. So I should have this entire voltage coming up. But note that that voltage is only for 90 degrees. It started with the peak and it has come until the zero crossing. So obviously it is there only for 90 degrees. We said that it has to conduct for 120 degrees, but it will not if I am talking about a resistive load. So if I am talking about a resistive load, because the voltage and currents will be in phase with each other, the voltage hits zero at this point, and after that the voltage will come out to be negative. Obviously I can't have the current in the opposite direction. The device will not conduct in the opposite direction. So at this point the conduction will cease to exist. It will stop at this point. So I am going to have the next one, which is again coming up. Will start coming up from here, and again I am going to have this entire voltage coming up. I want to reduce the voltage. For some reason I want to control the voltage. If I fire at alpha equal to 0, I could have used diode itself. Why should I use thyristor? I use thyristor only because I want to have a control over the voltage. So right now I am getting only for 90 degrees. So when I actually calculate the expression or compute the voltage, I should say VDC average in this case for R load and alpha equal to 60 degrees will come out to be integral of Vm sine omega t d omega t, no doubt, but it is starting from 90 degrees of VAN. So I should say it starts from 90 degrees and it goes until 180 degrees. That's all. This is for R load. Yes. Yes, if you give gate pulse at 40 degrees, it would have started conducting. This is alpha equal to 30. This is alpha equal to 40, slightly away. So it would have started conducting from here. So in which case this expression would also have changed. It would have started from 40. But whether it would continue beyond this, we have to check. He would have given the firing pulse for B also somewhere here. So until here, device number 1 would have conducted. From here, device number 2 would have taken over. I have just taken an arbitrary case. As simple as that. I am only taking an arbitrary case where I am showing the voltage to be discontinuous. Voltage is also discontinuous, current is also discontinuous for R load. When I exceed probably alpha equal to, 40, 50, kitna hai? If I try to exceed probably, this is 60, I hope I have not made any mistake. This is 60, right? Yes. So this happens to be discontinuous. Whereas if it is only 40, I would have still had, no, 40 is not here. This is 30. 40 would have been very much here. That will also be discontinuous. Even 40 would have been discontinuous. Only until 30 I will still have continuous. Because 30 means it would have started at this point and it would have come until here, 120 degrees. Again the next voltage would have started here, it would have continued. It is just touching 0. It will just touch 0. Right? Anything beyond 30 degrees alpha will be discontinuous for R load. We are talking about R load. We'll have to look at how RL load is. Okay? So now averaging still I have to do it over 2 pi by 3. Please remember this. Because I'm not getting any voltage all right, but every device is fired only for 2 pi by 3 interval. So obviously I can't average it over any other quantity. I have to average it over 120 degrees because every 120 degrees this particular pulse is being repeated. So I have to average it over 1 by 2 pi by 3. So this is what will be the value of voltage at this particular value of alpha, that is at 60 degrees. So at alpha equal to 60 degree for R load, this is how it will be. Let us try to take a look at the current. Is very simple. Current will be exactly the voltage wave shape because it is V by R. That's it. Nothing more than that. Right? Let us try to look at it for RL load. So this is for R load. Let us try to look at it for RL load. Right? So let me again draw the 3-phase voltages. Do we require that? Maybe. It's better to draw it. Okay. So this is how it is going to be. Right? I'm going to have the second voltage somewhat like this. And the third voltage somewhat like this. These are the 3-phase voltages. I am firing again at alpha equal to 60 degrees. I am taking as though we are firing at alpha equal to 60. So this is alpha equal to 0. So from here this is 30, this is 60. So I am going to fire at this point, and this point respectively. So here is where T1 is fired, here is where T2 is fired, and here is where T3 is fired. Right? So I am going to have, initially if I look at the current probably would start off from here in whatever way it rises depending upon R and L values. The current will start rising like this. And at whatever point IR equal to Pm sin omega t, if I say this itself is IR, for example, I and IR will be exactly similar, only a scaling factor. So, if IR meets with the voltage at this point, that is where the peak of the current will occur. So, the current is going to start coming down. So, if it comes down until here, I have shown as though the current is coming down until here, right? Obviously, the next phase current would start again similarly, and it might reach the peak somewhere here and then come down until here. Right? Similarly, I may have the third phase current rising and then coming down like this. So, I have just shown the three phase currents. Please note that because inductance is there, even beyond the negative, even beyond 180 degrees of VAN, the current could continue depending upon how much of energy is stored in the inductance. So, I will have the device basically conducting even beyond the 180 degree point of the voltage, which means that Vm sin omega t corresponding to VAN will be connected to the load until this point, until the zero of the current. So, I am going to have essentially the voltage coming up until this point. All this voltage will come up completely. Right? Are you getting my point? So, similarly, I will have all this voltage until this point. So, I should show again all this voltage, here. All this voltage should come up. This is how it should be. Right? So, this particular point, at what point the current becomes zero, I have to solve by the differential equation. There is no other way. So, I can write in this case Ia of alpha equal to 0. The current is Ia of alpha equal to 0 is the initial condition, and beta can be solved for again after deriving the complete expression for Ia or I should say in that if I say I of beta equal to 0, beta can be solved for. That beta is the final point where the current again becomes 0. It starts with the 0, ends with the 0. If I had larger inductance, then I would have had the current probably go to even higher values. And then I would probably see that it ends beyond, if at all I allow it to end, it would have ended beyond where the next device is fired. You get my point? In which case, I will not have 0 point at all in the current. The current is going to be always non-zero. If I have a larger inductance, I would have had the voltage, negative portion of the voltage coming up until here. Again it would have jumped to positive, then again negative, positive, negative and so on. So, if I say this is for RL load, I can have discontinuous conduction, in which case my output voltage will be whatever is my alpha to beta. I have to integrate between alpha to beta. And if I write this is Vm sin omega t, it is not correct. Why so? No, omega t equal to 0 corresponds to alpha equal to minus 30. So when I put the limits, I better be careful. I want to emphasize this. If I say alpha to beta is my limit for the voltages, please note this is omega t equal to 0. Whereas alpha equal to 0 is at this point. So this happens to be alpha minus 30, whether I like it or not. You get my point? That point happens to be alpha minus 30. Omega t equal to 0 is same as alpha minus 30. So, If I am saying actually from alpha to beta, I am actually integrating the voltage. I am integrating VAN. So VAN I cannot specify as Vm sin omega t now. I have to write it as Vm sin omega t plus 30. Yes. You have to write that as Vm sin omega t plus 30.